Okay, if I could have your attention, I'd like to start the session this morning. Welcome. There's still a dull roar in the room. Could I have your attention, please? Thank you. I'm Charlie Carter with AISC, and it is my pleasure to moderate or chaperone the session today. Chaperone, if any of you get out of hand, I have to take care of you. It's never happened before. So, thank you for coming. We have several segments to the session this morning, including the Beedle Award that SSRC presents and the Higgins Award that AISC presents. We'll start with another award, and I'm going to present it on behalf of my colleague Tom Schlafly, who is in charge of our research efforts. It is a faculty fellowship that we started a number of years ago. This is actually the 8th faculty fellowship that we've awarded, and we do generally one a year. So it's a very prestigious special award selected for a young faculty member that we would like to take an interest in helping to develop their career. It's been very successful at doing that, and we're very happy that this year the award is being made to Jason McCormick, who is at the University of Michigan. And Jason, if you would come up and receive your award. This faculty fellowship is awarded for work on seismic applications of hollow structural sections. Please congratulate Dr. McCormick on receipt of this award. The second segment of this session I will turn over to Ron Zemian, who's chairman of the Structural Stability Research Council, and he will make the Beedle Award presentation.
Oh my, lots of folks here. Well, good morning, ladies and gentlemen. I'd like to begin by once again thanking AISC for hosting our Structural Stability Research Council annual stability conference. It's been a major league success, and we really appreciate the opportunity to partner with AISC on this. As the chair of SSRC, I get to do a lot of neat things, and probably the greatest honor is to award the Lynn S. Beedle Award. A little bit of background on this award. Dr. Beedle was a longtime professor at Lehigh University. He was an international authority on steel and composite structures. He was really one of the fathers of the SSRC, an outstanding contributor for many years. He was also one of the leaders in the Tall Buildings Council. Back to SSRC, he really put us on the map and as one of the preeminent structural stability organizations worldwide. Several years ago, we set up this award in his name. The criteria for the award is you need to be a longtime member of SSRC. An absolute requirement is a worldwide leader on stability research. But just as importantly is a person who would foster cooperation between professionals worldwide and also have contributed not only to U.S. but international design codes in their development. And I couldn't be more pleased to announce that this year's award recipient, Beedle Award recipient, is Req'ts Behovta. If you have an opportunity to go back to your program, there's an excellent section all about Dr. Behovta and all of his accomplishments. I would take up all of the time of the T.R.C. Higgins Award winner if I were to try to go through them, but it's a very impressive career that he has had. One of the neat things is that he was a student of Lynn Beedle's when he was getting his PhD at Lehigh. He is a former professor at the University of Alberta, University of Pittsburgh, and the University of Arizona. He is currently a consultant. He is the president of the Behovta Group down in Tucson. He has been a longtime member and former chair of SSRC. Many of you also know him through his work with AISC. He has served on several technical committees as well as chaired a few, and he's also on the specification committee. He is recognized throughout the world for his scholarly work on column and frame stability, and also on the development of load and resistance factor design. He, as part of his PhD research and his postdoctoral research, he developed a series of column curves, which are really the basis for those curves that appear in several design codes, including our own AISC specification. So when you go to Chapter E and you design just a simple column and you see that equation, I hope that you'll think of Dr. Behovda. He has also, of course, worked on the Canadian and South African codes. He is the editor of the Journal of Constructional Steel Research. He has won numerous awards, including the T.R. Higgins Award, Shortridge Hardesty Award, which is a stability award, and the George Winter Award. And finally, I'd like to announce that he will be presenting his paper this afternoon at 1:45, session 9 over in the SSRC area. And the title of his talk is Columns from Single Members to Framework Members. So it is my great pleasure to award Radha Behovda the 2010 Beedle Award. Say a word or two?
It's I was a graduate student at Lehigh University for 4 years for getting my PhD, and I worked very closely with Lynn Beedle for several years. He was a driving taskmaster, but work got done with Lynn Beedle. So it's a unique pleasure to be able to accept this award named for Lynn Beedle. So thank you all. Appreciate your presence.
Well, it's now my pleasure to move to the next segment of the session, the T.R. Higgins Lectureship Award. And I'd like to start, there's a long history of the Higgins Award, and much of that history is in the room seated among you. I'd like all the past winners of the T.R. Higgins Award to stand, and we'll recognize them. So I'd also like to acknowledge this is an award that's selected by a committee, and I'd like to thank the members of the committee that participated. They are Bill Bast of Thornton Tomasetti, Dale Buckner of Virginia Military Institute, Judy Liu of Purdue University, Larry Muir, who is a consultant, Tommy Reeves of Alpha Industries, and Cliff Schwinger of the Harman Group. And we thank them for their efforts in selecting this year's winner. I'd like to begin by looking back as well at the history of the Higgins Award. And in fact, the very first winner was a gentleman named Igor Popov. Igor is no longer with us, but he lives on in many ways, including through this year's winner. Igor, in fact, was his professor and mentor. In the mid-1990s, I was secretary of the committee that Igor chaired on seismic design, and he mentioned to me casually that he would like to step down as chair, and he told me that he had the perfect person to succeed him, and he introduced me to Jim Malley, who is this year's winner of the award. It was my pleasure to serve as his secretary for a number of years and watch as his hair turned from the color it used to be to the color that it is now, as he worked through the Sac Steel project, took on the role as chairman of AISC's Task Committee on Seismic Design and shepherd of our seismic provisions, which a role that he still serves today as chair of that very same committee, a different committee number, slightly larger in size, the committee, that is. So it's my pleasure and also my honor and a personal joy to present this year's award to colleague and friend Jim Malley. Jim, would you? In addition to a very nice plaque, the award carries a $10,000 monetary award, which that will mail to you. This, I'm sure you can carry on your way home. Take it away. You just have to, if you get any questions at the end, repeat them into the microphone.
Okay, thanks, Charlie. Thanks for the honor of being here this morning. For those of you in the back, there are some seats up front. Feel free to come on up. Hopefully, we can, there's a little bit smaller room maybe than we needed to have this morning. But to start, this is a great honor for me, and maybe the best honor I've ever had in my career. As Charlie mentioned, the first winner of the award was Professor Popoff, who I was lucky enough to study with in graduate school. And so many of the other Higgins Award members I've looked up to as mentors and now have become colleagues and friends with. And so for me to join that group, I'm not sure that I deserve it, but I certainly appreciate the award and the honor of joining that group of people. So with that, the most important thing maybe for you this morning is the code, which is XP46K. And if you don't get it now, there's a couple more chances, so don't. If you stay awake, you'll see it 2 more times. So with that, let's get started. So the title of the talk is Seismic Provisions of AISC, Past, Present, and Future. And what we'll do is to sort of start from what I call the beginning and go back all the way to the 1920s. Very quickly to talk about sort of the infancy of seismic design, where we came from. I'll talk about what I would say, and that goes up to about 1985. I'll break that up in a couple pieces. And then talk a little bit about the recent past, maybe in the last 25 years or so, between 88 and 2005, as we sort of moved into more modern seismic codes. And I'll talk about the present and the near-term future, and I'm going to talk about those together. The present being the 2005 AISC seismic provisions, which those of you that are engineers working here in the United States using the International Building Code and doing the seismic design, you should be using that document every day. But I also want to talk to you about and inform you about what's coming in the near-term future in the 2010 provisions of AISC seismic, which are completed now and should be available for download on the AISC website within a couple months. So I think it's really important, though, to know what's coming, and so maybe some of the aspects of the new provisions you'd be able to incorporate in your designs now, because they won't be incorporated into the next building code and probably till the 2012 International Building Code. And then we'll speculate a little bit about the future. So the 2015 cycle that we're going to be working on AISC, as well as sort of maybe out beyond and where we're going with seismic design and steel structures. But before that, I would like to recognize the reason I'm here, standing before you today, is because I have the privilege of chairing what I call the hardest working committee in showbiz, which is the AISC TC9. We meet probably 2 to 3 times as many hours as any other AISC committee. And these folks are incredibly dedicated to making the seismic provisions as clear as they can be and as accurate as they can be. And I'm very proud to work with all of them. Few people that are there recognized with stars next to their name are the subcommittee chairs. The committee is so large I had to break it down into subcommittees. And the subcommittee chairs really carry a great burden and bulk of the load. So I want to especially recognize them, and Cindy Duncan, who's been our secretary for a number of years after she took over for Charlie. So as with the Higgins Award winners, I'd like to ask all of the members listed here as well as any corresponding members of AISC Seismic TC9 that are in the audience, please stand to be recognized. Come on, I know you're here. And again, thank you for all your hard work. I'd also like to recognize my company, Degenkolb Engineers, that has sort of unflinchingly allowed me to pursue this effort and the time that it takes away from business activities, and never really questioning whether or not it was a good idea for me or our company to do that. So I want to recognize and thank our firm. Okay, let's start then and talk about the beginnings. We'll talk a little bit about a couple earthquakes in the 1920s and 30s in Santa Barbara and Long Beach. Talk about the first really seminal document that was written on seismic design. It's called ASCE Separate 66. So ASCE has really been in this business for close to 60 years now. Talk about the SEOC Blue Book in 1959. Which really sort of moved that document into more of a code setting in the International Building Code. And these early days, we used terms like allowable stress design. And in the early days, we didn't even have any concept of ductility, or there was anything written in the code about ductility, or drift, or anything like that. It was basically designed to a force and hope for the best. And then I'll talk a little bit about the 1985 UBC, which I call the end of the good old days, and primarily because that was the first code that I sort of learned to work with, and it still holds a nice place in my heart. So the beginnings then, 1925 earthquake in Santa Barbara came on the heels of a great earthquake in Japan, the Great Kanto earthquake, and that led to the first Uniform Building Code in 1927, and actually the California Chamber of Commerce wrote a structural code at the same time, which I thought was quite interesting. I wonder if the Chamber of Commerce would be interested in such things today. And then the next earthquake was the 1933 Long Beach earthquake, which did severe damage to many, many school structures. And it led to statewide laws in California called the Field and Riley Acts that were really the first documents that made prescriptive requirements on the design of specific types of buildings, namely school structures. There were also the rudiments of codes developed in San Francisco and Los Angeles about at that time. The first base shear equation. This is from the 1937 UBC. Basically, you designed your structure for 2% of the weight of the building if you were on hard soil and 4% if you were on soft soil. And that was it. Wouldn't that be nice? The other thing I liked in this is that it recognized higher forces on wall elements, cantilever parapets, and the like. And even those non-building structures had their own place in this first table. And they had to be designed for 1.5 to 2.5 times what normal structures or buildings would be required to be designed for. So that kind of carried us to the 50s. And in 1951, ASCE Separate 66 was developed, first document, really, as I mentioned. First response spectrum, really ever kind of written into a standards type document or a guides document. Very similar in concept to the things that we're doing today with base shear design for elastic design. A coefficient of the weight of the building being the response that you need to design for. The K was to be determined in that document. So the system factor that we now refer to as the R factors, they said, well, somebody's got to figure out what to do about those. But we know that systems respond differently. But they didn't really put it into that document. And I was interested to see that they did put in a minimum base shear and said that no structure should be designed for less than 2% G. And believe it or not, we've sort of kind of come back to the future in ASCE 710, and we also have a minimum design shear that's not too far off of 2% G, although certainly the shorter period part of the spectrum is much higher than this one that's shown in Separate 66. So then we moved to the SEOC Blue Book, which for many years has been a great resource guide to the reasons why the code is written the way it is and the background for it and a kind of a commentary. In the 1959 Blue Book, the first set of K factors was written into that document, and that sort of gave us the design forces that we could use. Bliss here was there's only 4 different factors. So right now I think we have 85 different system definitions in the building code. But then you just need to know if it was a box structure, if it was a frame structure, if it was a dual system, or if it was a ductile frame structure. That was it. And then those non-building structures, they had their own category as well. So again, very simple, easy to determine which kind of system you had. There were some height limits put in there to try and make sure that engineers didn't kind of go beyond what people felt were sort of standard approaches. This was the first time that any ductility provisions were put into documents like this, and so ductile moment frames were described in this document. But there were no drift provisions, so we weren't thinking about deformation yet, still just all force. So now we'll talk about a 25-year period between 1961 and 1985. Updates to the code basically brought in more and more detail to the base shear equation. We started to come up with national maps that define the seismicity. And then in 1976, started to see an importance factor for the first time. So this recognized that some structures we would want to be operational after an earthquake. So this may be the start of performance-based earthquake engineering, when we started to define not just life safety and that as our intent, but trying to define some structures that would be operational after an earthquake. We brought the soil factor back out into the front and center of the base shear document. And this was the first time that we introduced drift. Early on it just said per accepted practice. Wouldn't that be nice? This is my accepted practice for drift control. Then they started into defining it as 0.005 times the height, and then using 1 over K depending on if you had a ductile structure or a more rigid structure. Again, but the length of the code then for seismic design was 13 pages, and that was on a small print document or small size document with large print. So you could learn that within a few days. In 1985, there were a couple of pages on steel design in the Uniform Building Code. There was one sentence that said, for brace frames, the only thing you had to do beside designing it using the AISC procedures was to multiply your brace frame connections by 25% over what the member was designed for. Again, trying to recognize, the start of recognizing that connections shouldn't be the place where we get failures in steel structures. Ductile moment frames had 1 page. We had some definitions on what materials were to be used, what to do about plastic design, the concept of designing for full capacity of the members and the connections, or demonstrating a ductile displacement connection approach. There was another about half a page on non-destructive evaluation and testing, so recognizing the importance of quality control in those structures, and that's it. Now 1985 isn't that long ago. It's only 25 years ago, but as I think you'll see in the next set of slides, we've come a long way since then. So we'll talk about the recent past then, the last 20 years or 25 years or so. ATC 3 was the landmark document that came out in the late 1970s that sort of set the basis for all the modern codes that we're working with today. And we can trace back the majority of what we've done to ATC 3. The 85 NEHRP provisions developed by the Building Seismic Safety Council and the 88 UBC started to incorporate that information into their documents. We switched from allowable stress design to a strength design basis. R factors replaced K. We started to put in uniform hazard for ground motions. And then started this proliferation of system definitions. This is when that all started to jump into the fray, with the idea that we needed to be very specific about our different systems and the kind of performance we wanted to get out of them. This was the first code where a capacity-based approach was introduced, and that was for the eccentric brace frame system, where we had a rational approach to making sure that we could follow a capacity design and I'll talk a little bit more about that as we go forward. In this time frame as well, as Charlie mentioned, AISC put out its first edition of seismic provisions as seismic sort of made its way across from the West Coast to the rest of the United States, and Professor Popwak was the chair. After the Northridge earthquake, we sort of rapid fire tried to update the provisions as quickly as possible. We actually made three updates between 1997 and 2000, and then another edition in 2002. So we were trying to update a lot of the research that was going on, the testing and the development of new information, and get it in the hands of practitioners as quickly as possible so that we wanted to make sure that you were doing the best job that you could as soon as possible. We now are fortunate, I think, that we have one set of provisions that covers the entire United States for seismic design. So in the old days, there were three kind of competing codes, and there were different standards, and people did things differently. Now, if you're designing seismic structure wherever you are in the United States, you're pretty much going to be using the seismic provisions. So let's get into the meat of the presentation then, and that's the 2005 and 2010 seismic provisions of AISC. As I mentioned, 34105 is incorporated into this 2006 and 2009 IBCs, as well as ASCE 705. We just completed ASCE 710, and that'll be in the 2012 IBC. In the slides that are coming, what I'm going to be showing in white is what's in the 2005 provisions, so that's what should be on your desk right now. And then in that goldenrod color, it will be what I call the coming attractions of the 2010 provision. So trying to get you to think about a little bit of what the committee was working toward to try and improve the provisions the next time. But first, let's talk about the philosophy of AISC 341. There's really three parts to it, and it's pretty simple, but I think if you keep these three things in mind as I talk through the rest of the detail, you'll be able to pull yourself back to what this provision is trying to deal with. Is it dealing with the target yield mechanism that we've identified, and we're trying to make sure that each of our seismic load resisting systems has a target mechanism that we can work with. The designation of our deformation controlled elements or our ductile fuses. These are the places where we want to dissipate the energy of the earthquake that it inputs to the system. We designed those for the base shear equation and the reduced forces that come out of ASCE 7, and then put in as much ductility as we reasonably can. And I've heard that the term said you can never be too ductile, and that's probably good for these elements, but we do want to try and make sure that we do it within reason as far as cost goes. These are fairly prescriptive provisions. Basically tells you, here's your B over T ratio, here's how often you need to brace it, here's where you need to put stiffeners and the like, so that we make sure we get that energy dissipation locally. Then the last piece is the capacity design piece. So the rest of the system, once we've identified those fuses in the building, we design the rest of the system to remain essentially elastic for those forces. And so we need to look at those both locally as we connect to one of the fuses, or globally if you're a column that's supporting a number of shear links and eccentric brace frames up the top of the building, you need to recognize the force in that column is going to be affected by the capacity of those links above it. And this is an area where, even though the code is fairly prescriptive in many ways, there still needs to be a lot of judgment exercised. And this is the area where a lot of thinking needs to go forward to make sure you get a good design. So it's this simple. If you develop your target mechanism, and you put in the ductility requirements on your fuses, and you put in the capacity design correctly, then you end up with the AISC seismic provisions. So the target yield mechanisms for a couple of systems are shown here. Moment frame on the left. The ductile elements are the ones that are shown in red, with the hinges or the locations of plasticity shown in sort of either yellow or with circles. The center is a brace frame where you've got the buckling member and the yielding member in tension, and the one on the right is the eccentric brace frame with the shear link. So think about these things as we move forward. Okay, let's go through and summarize the basic elements of the 2005 provisions. It's broken up into two parts. The first part covers structural steel. The second part covers composite construction. It's generally intended for seismic design categories D, E, and F. And if you, hopefully you work with ASCE 7 as well, that's sort of the areas of higher seismic demand throughout the country will be in those categories depending on occupancy and location, etc. It's very well coordinated, we think, with ASCE 705. We've tried to bring together all of the research that's come out of the FEMA SAC project to make that happen. And one of the things that, parallel to AISC 360, we put this into what we call the unified specification format, where both the load and resistance factor design and now allowable strength design are both in the same location. So we've got those into one set of provisions, so you don't have two sets of kind of competing provisions. Talk a little bit about the major changes for 2010. We've reorganized the document to be more consistent with AISC 360. So you'll see parallels when you're working with the main specification and AISC 341 that you probably wouldn't have seen previously. One of the major things I think that's going to help with sort of some of the transparency of the document is the system definitions and approaches and the way they're dealt with are very consistent for each of the systems. And I'll get into that in a little bit. We've been able to incorporate AWS D1.8, which is the seismic welding code, which wasn't available to us in 2005. We had to put a lot of their information into the 2005 provisions. We've now been able to pull that out and reference AWS D1.8. So our document's actually a little smaller, I think, than it was previously, which is kind of a unique thing for seismic codes. We also brought composite construction and kind of eliminated this idea of having two parts. Parts 1 and 2 no longer exist. So we treat the composite construction systems right in with the rest of the steel systems. There was a lot of work that had to go into making that happen, and I want to recognize Jerry Hajar, who's the chair of that subcommittee, because they really had a lot of work to do in order to bring the composite provisions into Part 1, so thank you, Jerry, for that. The other thing that's, I think, a big move forward that I'm going to talk about for a few minutes is developing design and analysis provisions that explicitly follow a capacity design approach for all the systems. As I mentioned, eccentrically braced frames was sort of the first one that got kind of really into capacity design, and then we sort of chipped away at all the other systems, but there was a couple of systems that still hadn't gotten there. And for the one I'm going to talk about is special concentric brace frames, where we've made some new requirements on analysis that really will give you a better feel for the expected performance of that system. We did our usual updating of member and system requirements that come from new knowledge from research or testing or the use by, comments that come from practicing engineers. We love to get those about how they're using the document, if things are not clear or not, or if they think there are holes in things that we've put together. And then we coordinated, obviously, with ASCE 710. Okay, let's talk about the scope and general requirements. It's generally intended and it's been developed for buildings, and but we also have language that talks about it being also applicable to building-like non-building structures, an interesting term. But what that means is really structures that have vertical frames and horizontal diaphragms of some sort that deliver load to vertical frames in a way like similar to buildings. There are other structures that it doesn't apply to, transmission towers and tanks and things like that, which you have to go other places to deal with, even though they do have steel in them. There's a glossary that develops or the concepts of the entire system. It's not just the vertical frames, but also horizontal diaphragms that are delivering seismic load into those frames, collectors and cords, etc. In seismic design categories A, B, and C, the lower seismic zones, if you somehow had to design here in Florida for seismic design, you're in seismic design category A. If you, for some reason, wanted to use AISC seismic, you could do so, but you also have the choice of using the main specification with an R equals 3 and not having to go through all the provisions that I'm going to talk about here for the next few minutes. In most cases, I think that's going to be the wise choice. The benefits you get of using the seismic provisions in categories A, B, and C is that you use that higher R factor, so your force levels are lower, so potentially your member sizes are smaller, but not necessarily a cheaper structure to build. In 2010, what we did in the scope area was to develop more clear documentation about how we coordinate between ASCE 7 and the seismic provisions, and we're clarifying the use of ACI 318 for composite systems that have reinforced concrete elements in them. On general design, we refer to ASCE 7 for height limits and seismic design categories and story drifts and the like. In the 2010 provisions, we did a better job of clarifying how to use the amplified seismic load provisions that you have to apply in certain elements of the system, again, to make sure we get that capacity design approach taken care of. We also talk about how to approach the required strength on every element in the system, whether it's required from the analysis of the system based on ASCE 710, and that would be for your ductile elements, or if it's from the capacity-based design approach where you define a capacity of your ductile elements and then apply it to the rest of the system that's supposed to remain essentially elastic. And then some more definitions on how to apply LRFD and ASD. One of the things that was, I think, a major step forward in the 2005 provisions were the requirements on project documentation. And this was an area that actually AISC 360 has now followed up with in the 2010 edition in their Chapter N. This idea that we really need to do a better job of documenting both either if it's a design drawing that I put together as this engineer record, or the shop drawings that the fabricator puts together to validate or verify that he's understood the intent of my design. Same thing for the erection drawing. So there's a very specific set of rules, or not rules, there's a list of items that need to be included in the various documents in order to make sure that you've covered everything in your presentation, so that hopefully that will eliminate any misunderstandings between the various parties, or not any, as many as possible, between the various parties, and hopefully improve the quality of construction that gets put into the field. So let's get into the spec itself, talk about the materials. Basically, any material that's covered in AISC 360 is pretty much allowed in AISC 341. Steel is a ductile material, so we really haven't seen the need to put too many restrictions on the basic structural products. One of the things that we have done, again, this concept of capacity design is so important to us that we need to really not just work with minimum specified strengths, but expected strengths of steel. So if you're a grade 50 material, that's a minimum. The expected capacity of that, the mills are going to make it a little stronger, so when they do their certification tests, they don't have to chuck a whole heat of steel. So usually you'll find in most of the materials for the structural wide flange shapes, maybe it's 10%, HSS maybe 30 to 40% higher than the minimum yield. We also use the tensile strength and get the expected tensile strength. And the reason we need this is, again, defining that capacity of those ductile elements. We need the real capacity, not the minimum specified capacity, in order to properly design the rest of the system to be able to make that fuse occur when the earthquake hits. So we talk about available strength, etc., and trying to ensure that we're getting ductile modes of failure. For heavy shapes and plates, we have requirements on V-knot Sharpie toughness of the base materials, similar to what was developed in AISC standards for large truss elements in the 80s. It's a little bit more restrictive than those basic requirements for Sharpie V-notch toughness on the thicknesses. But again, it's just something we need to check when we get to very large members. In 2010, we've expanded the use, or the allowed use, of steel beyond grade 50 to grade 65, which has become more common in column shapes, etc. And then again, referencing excuse me, the AISC or AWS D1.8 for filler metals, which now we can put that material all in their document. So we'll talk for a couple minutes about connections and joints. In bolted joints, Generally, we're looking at fully tensioned high-strength bolts for Class A slip-critical preparation of the joints, but design them for bearing. So we're designing them for bearing, but preparing them for slip-critical. You probably say, why would you do that? The idea there is that the recognition that in the smaller earthquakes, we don't want to have a lot of slip in the connections, so that's why the slip-critical preparation, but recognizing that when we get to that major earthquake, the bolts are going to slip into bearing, so let's take advantage of that complete strength. We also don't allow sharing of load between welds and bolts in the same line of action. Doesn't mean an entire connection can't have welds and bolts, just means if you have one force, you can't have bolts and welds sharing that force because there's deformation and incompatibility there that you'll never be able to kind of add those two together at the same time. Generally standard size holes, although we can use oversized holes for braces to allow ease of erection and construction. In the 2005 provisions, in addition to designing the connections generally for the capacity of the connected member, we also required you, kind of a belt and suspenders idea, if you will, to demonstrate a ductile limit state. So when you went through and checked all your limit states, you couldn't have a fracture type limit state. You needed to have a yielding type of limit state. So it basically, in some cases, required even an additional safety factor on top of the capacity design. We've removed that in 2010, so we've actually made it less restrictive. So we will do that if we think it's the right thing. So hopefully that will, and I think that will make it easier on many of the connection designs, that especially those that use bolted connections. Let's talk about welds for a little bit. In 2005, we didn't have AWS D1.8 yet, so we had an Appendix W that covered a lot of the material that's in D1.8 related to how we weld, what do we do with backing bars, etc. We were able to incorporate that in 2010 using the AWS procedures. And there's things about welding procedure specifications and continuity plate detailing, etc., that's going to help us, again, provide that ductility that we need. Welded joints in seismic frames all have to have demonstrated toughness in their welds. Every weld in a seismic system needs to have a minimum level of toughness. Right now we're at 20 foot-pounds at 0. This came out of the FEMA SAC research. For very special welds, we call them demand critical welds, which are right next to areas of high inelastic demand. We do something called, obviously, a demand critical weld. Those have two levels of toughness specified, one at 0 degrees and then basically 40 foot-pounds at 70 degrees, which again came out of the SAC research in the 90s, and that's in order to demonstrate a level of toughness up at this sort of service temperature of the structure. That's now all taken care of in the D1.8 provisions in 2010. The other part of welded joints I want to talk about right now is the protected zones. And again, think about those hinges I showed in the target yield mechanisms. Those are the areas that we're going to be straining well beyond yield, 4, 5, 10 times yield strains in some of those locations. And we need to make sure that those are going to be there and perform for us. So what we've done is said that these are like no-fly zones, if you will. You need to really be careful that you don't disturb the steel in that area, let it do its job and perform with that ductility. So we've said that you can't have anything like an attachment for a curtain wall or shot pins for a metal deck. The only thing you can do is put in some small spot welds to hold down the deck for OSHA requirements. And the figure or the picture on the upper right there is the top flange of a beam that was tested at Lehigh with a composite deck that you can see a fracture that went right through the entire top flange. Right next to the shear connector that was placed inadvertently over the middle of the plastic hinge region. So we want to avoid that if we can. And we also, if you do end up with that in the field, and I think many of us that have done these kind of systems have run into places where the plumber didn't know there was a protected zone and he just went through and hooked something onto the structure. We have to work with the contractor on getting those repaired properly. We're required as engineers to, on our drawings, document where are the protected zones, and make sure that in a lot of cases, putting signs on them to say do not disturb, things like that, to make sure that those are there for us when the earthquake hits. Talk a little bit about members. The width thickness ratios are often more strict than the main specification for members in seismic systems, and I'm going to talk about that with this slide. This shows kind of the graph of the moment capacity of a section as you go sort of from the right to the left, from elastic buckling to inelastic buckling, and then kind of peaking out there with plastic buckling. And down below you can see sort of a chart of ductility and how that varies with width thickness ratio of the member. So with seismic design, we're really looking in those ductile elements, those deformation controlled elements, we're really focusing on the pushing ourselves as far as we can down the ductility curve. So we're lambda PS, we call it, which is less than lambda P, or the plastic limit, which is sort of the break point between plastic buckling and inelastic buckling. So we use sort of 3 different levels in the seismic provisions to recognize that. In 2010, to try and make it again more transparent, we came up with the terms moderately ductile and highly ductile elements. And again, your highly ductile are going to be in the high ductility systems with the high R factors. Those elements that are plastic, going to be plastic where the plastic hinges are. So beams and moment frames, link beams and EBFs, braces and special concentric brace frames, those sorts of locations. The moderate ductility are going to be elements that are part of maybe the capacity designed elements in the higher ductility systems, and the yielding elements in the low ductility systems like our ordinary systems, and I'll talk about that in a little bit. We also use those terms to flag now the bracing requirements, the lateral bracing requirements, to make sure we have stability of those elements, which obviously is important, as well as the ability to form the local plastic hinge. We've incorporated some new sections in this 2010 provision for HSS and box slide flanges, as well as composite elements. The provisions also now have a small section on diaphragm design, which is kind of, we've sort of not dealt with in the past, making sure that we're properly coordinated with ASCE 7 and ACI Chapter 22 to make sure that that load transfer from the horizontal elements to the vertical elements is properly taken care of. I mentioned bracing requirements are now uniform across the systems. Again, this sort of fell out of every system being defined very specifically and consistently. We were able to nicely make sure that we were consistent on the bracing requirements. In 2005, and this sort of goes way back into the provisions well beyond AISC seismic, columns with high axial load were checked for amplified seismic loading conditions. In 2010, we've actually said just check the amplified loading conditions for all columns. It comes out of the computer, it doesn't matter, all the load combinations are there, just go ahead and do it that way. It's not going to change the design any. We also have those requirements included for the composites. Column splices and bases are a very special category of connections. Obviously, one of the things you really want to avoid is any kind of a column fracture or splice fracture, because if you lose one of those, you could lose a whole building with just one connection breaking on you. So it's something we were maybe intentionally a little more conservative than on other elements in the system because of the ramifications of possibly losing one element or one connection. So we've got some very strict requirements about the use of partial penetration welds and the forces that those are designed for, how you transition the welds, etc. The other requirement on column splices that's a unique one is that all columns in the building are covered by this element. Even if it's just a gravity column, we have a requirement on the design of the shear connection of those splices to make sure that we have continuity up the height of the column. And this is the only place where we deal with the gravity columns at all, or gravity system at all, in the seismic provisions. And the reason for that is that what we found from a lot of nonlinear time history analysis is that if you incorporate or include that resistance of those columns and their continuity up the system, you get an additional strength and stiffness. Then it's low, it's not very big, but you do get an additional strength and stiffness that's not included in your design. And what we found from these nonlinear analyses is that just that little additional strength and stiffness will help you to avoid weak stories where you concentrate all the inelastic demand in one floor, and you're able to better spread the load through multiple stories. So that's why that provision is in the code. In 2010, we've worked on clarifying the language a little bit and referring to D1.8, as I mentioned, and talked a little bit about column base welds. Column bases is another area that's important design consideration. Basically, here it's fairly simple. We want you to design the base connection into the foundation, or the connection to the foundation, for the same force that the member above it is designed. And so shear, moment, axial force. Yeah, this is where sort of the interaction with ACI 318 Appendix D occurs, and there's some clarifying language there. Another new provision in 2010 highlights the need to verify deformation compatibility of the gravity system, the ability of the gravity system to go through the drifts that we designed the building for, and make sure you don't lose gravity capacity at the design story drift. And this is really put in large part to put in a user note, which is not part of the code, but should help the engineers understand that basic shear tab connections in our steel systems have been demonstrated to go through very large drifts. So you don't have to do lots of calculations or justification in a steel building to make this provision work. But we wanted to highlight that there so you didn't run into a plan checker that said, well, where's your deformation compatibility check? And now you know that all you have to do is say, there's test results for shear connections that say I got more than enough deformation compatibility in my gravity frame for steel. So before talking about the systems, I'd like to talk about the formatting that we've done in 2010, because I do think it's going to help clarify and make more transparent the system definitions and the ability to compare systems across as you're trying to decide between an eccentric brace frame or a special concentric brace frame or a buckling restrained brace frame. You'll be able to compare the different system definitions like line by line and then make a rational decision. So there's a scope definition, a basis of design. This is where we're defining our yield mechanism and our protected members or our ductile members, our fuses. There's some information about the analysis that you need to do. System requirements, this is the lateral stability bracing, system-wide requirements, forced deformation demands. The B over T limits for members, again, ductility provisions, protected zones I mentioned before, and then the connections, obviously a key element of any seismic design, defining the demand critical welds and splices, etc. The other new chapter in 2010 is a very short chapter. It's more of a placeholder. I think over time it may grow as we develop more definition here. It's on analysis. We've got some very short definitions about what section properties should be used for both steel and concrete in the composite elements. And it refers to, it sort of has a pointer to the demands or the design requirements for the systems related to analysis. There's also a pointer to ASCE 710, Chapter 16, which has had a major update related to nonlinear response history analysis, that when you do choose to do that in your seismic design, you're supposed to use that set of provisions to go forward with. So for those of you that are still awake, the code is, and those of you that walked in and didn't get this the first time, the code is XP46K. I'll take a drink of water here. So let's talk about special moment frames. We'll go through the systems now. Basically, this was the hot element after the Northridge earthquake, obviously, with the damage there. We now have provisions that require tested results on our connections there. Generally to 0.04 radians for drift. There's 3 different ways of making that happen. Either you test it for your project, or you go through an appendix pre-qualification, or you design them in accordance with AISC 358, which I'll show in a second, is a new standard that pre-qualifies a number of connections, and then you won't have to go through any additional calculations. In addition to the moment design of the connections, we need to develop the shear connection at the moment frame joints to develop those full plastic capacity of the beam at both ends. A little bit about that pre-qualification standards, titled Pre-Qualified Connections for Special and Intermediate Steel Moment Frames for Seismic Applications. Ron Hamburger is the chair of the committee that develops that, and we work closely with Ron to coordinate what they're doing with what we're doing. It allows you as an engineer to pick a connection out of that document that's within their limitations of height and size and thickness and plates and the like, and submit that with no further calculations except what's required in their document to justify your design. They're just about completed with their 2010 edition, which incorporates additional connections beyond the reduced beam section and end plates that were developed for the 2005 provision. And they're continuing to work on a number of other connections over time to get pre-qualified to make it a little easier on us. Other elements of special moment frames that are important to the design, first is obviously the panel zones. We want those to be as ductile as we can be. The provisions are intended to balance the yielding in the moment frames and get some panel zone yielding as well as beam yielding. We want to spread the yielding as much as we can to take advantage of the ductility of the steel. So there's requirements on how you calculate that, how you put together your doubler plates, either against the web or separated from the web. And there's detailing requirements, tells you how to provide that ductility of the system. Another major element for special moment frames is our strong column weak beam check. Again, wanting to avoid weak stories that are going to concentrate the inelastic deformation in one story. We check that on a column by column basis, so it's sort of an indirect check of weak stories. And in 2010, we've done some clarifications to the language to make sure that you check the columns and reduce their capacity for bending by the axial force induced by the amplified seismic load. So again, if you're doing that for 2005, you may want to think about the fact that the axial force in that is going to be higher than what comes out of the standard building code requirements. Column splices in moment frames, we've really pushed toward CJP welds, so complete joint penetration welds. And the reason is the little graphic at the bottom left is sort of a simple portal frame where the inflection points are sort of near mid-height of each story. And your splice usually is going to be a couple feet below that, so you think, well, maybe, the demands on those splices are not going to be that great. Why would you need complete joint penetration welds? Well, what we found, again, from these nonlinear response analyses is that in real ground motions, the plastic hinge is moving up and down within a story kind of all over the place during the ground motion. And in some cases, you don't get any plastic hinge over a full column height. So in those cases, you could get quite large moments approaching the full capacity of the column. So that's why we've been fairly conservative, again, because of the potential impact of losing a column connection. Lateral bracing of beams, obviously, if we're really pushing these moment frames hard and wanting to get a lot of ductility out of them, we need to recognize that we need to brace them laterally so we don't have any stability issues. So the requirements for both bracing along the length of the beams as well as at the plastic hinges. The force at the plastic hinges is quite large. It's about 6% of the capacity of the flange. So think about AF, AS, FY on the flange and multiply that by 6% and then try and push that back into your diaphragm, and it's something you can't ignore. It's a big number. You need to keep them out of plastic hinge zones in this slide here. Unfortunately, that wasn't properly communicated by the design engineer. They put the lateral brace right in the middle of the plastic hinge, so not really the best idea, especially since it's a protected zone area. Generally, you want to move those lateral braces about maybe one flange width beyond where you think the end of the plastic hinge is. The other couple of standard moment frames are intermediate and ordinary. The provisions on those are less restrictive, primarily because the code requires you to keep those or doesn't allow you to use those in all the applications. So there are height limits and weight restrictions and the like on those structures. So we reduced the connection requirements for the intermediate down to 0.02 radians. Moderately ductile members instead of highly ductile, which we use for special moment frames. We do now require demand critical welded splices, again, for the reasons I've been mentioning. Ordinary moment frames you can actually use without any connection tests, so you can do it by calculation. Again, very limited applications for those, one-story buildings, very light buildings generally, where you can use that. if you don't use connection tests to demonstrate your capacities or your deformation capacities, we have a set of detailing requirements that includes access hole configurations like the one I showed here, which will help to avoid any kind of premature fractures in those connections. Another moment frame is the special truss moment frame, been developed in conceptually very similar to eccentric brace frames, with the ductile steel segment shown in the middle of the bay of those, the frame on the upper right. You can do it in a couple different ways, whether it's a kind of a crossed diagonal with light plates or a Vierendeel approach. We've limited the application of these based on the tests that have been done to spans of about 65 feet and depth of the truss of about 6 feet. So you can't use this on the Cowboys Stadium or anything like that for long span type structures. We've done a little bit of editing and clarification in 2010, and again added demand critical column splices. We've added 2 new systems to the document, short additions for cantilever columns. These were again came out of ASCE 7-10 in the past. There have been cantilever column requirements or definitions in ASCE 7, but we haven't really dealt with it in AISC. We felt like it was important for clarity to do that now. So we have an ordinary and a special system and requirements on axial loads and B over T limits and connection demand requirements for the special system. So pretty simple if you do have those cantilever type column type structures. Talk a little bit about brace frames. First one is special concentric brace frames, which is a fairly ductile system, are usually in the 6 range. Some basic requirements for KL over R to make sure we've got good stiffness in our braces, but not too stiff. B over T ratios are quite strict on the braces. Again, those are our ductile yielding elements. And connection requirements. Obviously, we don't want the connections to fail, so they're designed for the tensile capacity of the sections. We've got requirements on chevron and K-bracing. Basically, we don't want K-braces where the braces come into the center of a column between floors because of the potential out of plane force that could be induced into the columns. The chevron braces are shown on the lower right there, and the idea there, when the compression brace buckles, the tension brace still wants to pick up additional force because it hasn't yielded yet. So there's a downward pull on those beams, and so there's requirements in 2005 about how you design the strength of those beams to take that unbalanced force that comes from the compression and the tension braces. In 2010, we actually put in this 2-level analysis, which I'll talk about in a second, and increase the requirements on the connections at the brace frames. And the reason we've done this is that we recognize from analysis of these systems that the real rotations and displacements that you're going to see in these connections is well beyond sort of the elastic level. We're talking 2-3%. So you need to demonstrate that your connections can go through that drift either with calculations or with test results. And similar requirements are for all the primary brace frame systems, the eccentric brace frame and buckling restrained brace frame. And again, we've upped the requirements on demand critical welds on the column splices. So let's talk about this new analysis requirement, because I think it's an important conceptual thing to think about when you're thinking about concentric brace frames. In the past, you would only have been required by the code to look at the analysis distribution of forces on the left, where you're elastically analyzing the frame for the forces that come out of the building code, and in compression and tension, basically the forces are going to be very similar. So if you looked at a 2-bay brace frame like this, it would tell you that there's no lateral force in that center column, and no uplift on that center column, maybe in your foundation. But think about the reality of nonlinear inelastic design for seismic. If we do overload those braces, we're going to buckle the compression braces, and those tension braces are going to try to continue to pick up load and continue to resist that force and resist the displacements. So what we've done is said you need to also do an analysis that recognizes that after buckling of those braces, you're going to get a reduced capacity and compression for those braces. And you're going to get this unbalanced force at the various locations where braces intersect. So the residual capacity of those braces we define as 30% of the original compression capacity, and that's based on a lot of test results and looking at the kind of requirements that we put on K/R and V/T. So in that case on the right, then now you look at those unbalanced forces, and now you have quite large forces in that center column. And the distribution of force is completely different, not completely, but very different from what it is on the left if you take the forces through the entire frame. So you really need to look at the design for both systems, both lateral force distributions. The exterior columns on the left and right of the frame will be controlled by the system of distribution of forces on the left. The center column will be controlled by the right. The other thing to note is the large shear that's going to be generated in the beams for the distribution of forces on the left, and that's similar to what we required in 2005 with that unbalanced force that occurs at the center of the beams where the two braces come together. So again, I think even though this isn't in 2005, conceptually for your target mechanism, you should be thinking about both distributions of forces when you're trying to size your members. Okay, we'll go to the less ductile brace frame, ordinary concentric brace frames. These are limited for use in high seismic design categories. Again, low-rise systems, 1- and 2-story buildings primarily. Connection brace is generally based on the amplified seismic force. We've gotten some clarifying language in 2010. There's restrictions on compression or chevron bracing similar to the special frames. We do allow tension-only braces in some applications for these systems, and that will allow you to do penthouses and the like with rod braces if that's appropriate. And again, no K-bracing is allowed in the 2010. We also define that you can use minor eccentricities in the connections if that's going to make the connections more efficient, but obviously you'd have to take those eccentricities into account in the member design. Eccentric brace frames, again, I mentioned a couple times, primarily done using a capacity-based approach. Identify those link beams, design the braces in columns to remain essentially elastic for those capacities. Generally, you're going to be using shear links, links that yield in shear, and they're going to have some pretty extensive stiffening requirements, again, to provide the ductility that we think we need. In 2010, the big changes were to bring in some work that was done at the University of Buffalo by Michel Bruneau on built-up boxes, and to clarify some of the calculations that are done for displacements in the system, and some of those similar changes on column splices. In the EBF provisions, we also have requirements on connections where the link is adjacent to the column. Sort of frown on that because you are going to get some very large demands there if you do have to bring your link into the column, like the slide on the upper right, or the picture on the upper right. Generally, we're requiring that you have connection tests to demonstrate your connection. Otherwise, you're required to basically stiffen the connection so much that you're basically pushing the link away from the face of the column to avoid any kind of fracture. The beam outside the link and the columns need to be designed for the capacity of the link and strain, including strain hardening and that expected yield strength I talked about earlier. For the braces that are connected to one beam or one link beam, those are required for a strain hardening factor of about 1.25. Columns, which is kind of graphically shown here on the lower right, are designed for about a strain hardening factor of 1.1. So the column at the base there where it says PU has to be designed for all three of those links yielding and strain hardening to 10% over their expected capacity simultaneously. Okay, so that's going to create a quite large load. It is probably very conservative as you get into taller structures. For short structures, it seems to work fairly well to look at it this way. Again, lateral bracing, this is a high ductility system, so we are going to be bracing laterally. At the ends of links, you get large demands like at plastic hinges and columns, so we have that 6% limit again. And then you also have a stiffness requirement as well as strength. A new system in 2005 was the buckling restrained brace frame system. It improves on special concentric brace frames because it provides a ductile brace response, so we aren't going to get that reduction in capacity in the compression side. The concept is that the brace is within a stiffening element so that when it wants to buckle, it is restrained from that buckling by the collar around it, if you will. If you look at the graphic on the upper right or the slide on the lower right, you can kind of see what that looks like. It was developed in Japan. They traditionally use it there as more as damping elements than braces. We've chosen to use them as braces in the U.S. You basically can get hysteretic behavior like perfectly elastic plastic material. So this was developed in some joint efforts with various committees like AISC and CEOC and put into the 2003 NEHR provisions as well as the 2005 AISC Seismic. Because those steel cores are such important elements, we require that they be demonstrated and tested for twice the designed story drift. There's an appendix in the document in 2005 that tells you how to do that. There are a number of exhibitors downstairs that provide these braces that you can learn more about how that's done down there. It's actually interesting that in compression these braces actually are stronger than in tension. There's a little bit of stiffening that goes on in the core, so you actually need to design the compression capacity a little more than the yielding capacity in tension. The nice thing about them is you don't have to oversize your braces for compression, so your foundations can get smaller and columns can get smaller, and you also don't have that unbalanced force effect with chevron braces because you don't get that buckling and reduction in capacity and compression. Again, like the special concentric brace frames, in 2010 we increased some of the connection requirements for drift and the demand critical welds on the column splices. The other new system in 2005 was special plate shear walls. This initially was developed in Canada. It's been in the Canadian code for a number of years based on research all around Canada by Jeff Kulak and some of his colleagues. It's also been studied at UC Berkeley. So the idea here is that you're sort of getting almost like a plate girder approach, very thin plates in relation to the size. They're going to buckle as this test specimen did here on the right. We required some panel size definitions in the 2005 provisions to make sure it was consistent with the tests. We also require that you put boundary elements around any openings to make sure that you're getting yielding and ductility in the plate and not in the surrounding elements. We require that the connections of those plates to the rest of the system are develop the full capacity of the web plate. And in kind of similar conceptually again for this capacity design approach, lateral bracing requirements for the beam. Again, you're going to get some ductility and out-of-plane forces or deformation demand out of plane that the ductility is needed or stiffness is needed in your braces. In 2010, we added a couple of new elements based on some research again on perforated webs and webs with corner cuts. So at the corners, we saw a very high stress concentration. So there's some ideas for having a semicircular corner cut to avoid that. Perforated webs allows you to keep the capacity down. We found is that the reasonable plate thicknesses, you're going to get such large capacities that it really ends up oversizing the columns and beams in the system in order to get the base shear capacity. So the perforated webs helps to pull that back down to a reasonable level. We added some protection zone requirements next to connections, and again, similar things on the demand critical welds at the splices. Unfortunately, I don't have a whole lot of time to talk about composite systems. If you were yesterday afternoon, Jerry Hajar gave a very nice talk on the new requirements for composite systems. I will say that there was a great effort to make those go forward into the 2010 provisions, and it's greatly updated. So if you are using composite provisions or the composite systems now, I would really recommend that you use the 2010 version because there's a lot more detail and it'll be a lot easier for you to execute those designs than with the 2005 provisions. There's a number of different systems. Again, same kind of ideas of capacity design of connections between composite elements and steel elements or composite elements and concrete elements, etc. So again, check out those two areas. On quality assurance and quality control. So now we've designed all of our systems and connections and we've done the best job that we can to make sure we've implemented all the provisions. We now need to make sure that gets properly put together in the field. So we put together an Appendix Q for quality. that develops a set of requirements based on a lot of the work that was done in the FEMA 353 project, out of our FEMA project, and documented in the 353 document of FEMA in 2000. It calls for both quality assurance and quality control and requirements for documentation of different elements. It talks about the inspection requirements and different types of inspection, whether we call it observe, perform, and document. So observe is your sort of periodic type of inspections where the inspector needs to be there and make sure the welder's got things set at different times. It doesn't have to be looking over his or her shoulder all the time throughout the performance of the welding. Perform is more akin to continuous, although it's not intended to be absolutely continuous for every weld. And that's sort of listed for very special elements of the design, such as complete joint penetration welds. And the locations of non-destructive testing are required for both ultrasonic and magnetic particle. We augmented this in 2010 with the provisions for composite construction. So again, very parallel now. And I think this is, again, I mentioned before, the Chapter N of AISC 360 has sort of followed this document in bringing quality directly into the AISC specifications. So that's the provisions. We'll talk about kind of where we're at. Again, ASCE 705 is in 2006 IBC. We're done with 2010, and it should be available shortly. Believe it or not, our first meeting of the next edition of the provisions is coming up in July. So if you do have any suggestions or comments about the provisions now, please get them into us. We're going to be starting on our next round of updates and hopefully improvements to the document. So we're always looking for your suggestions as the users of the spec. So let me spend the last 10 minutes or so talking about where we go from here, and some ruminations about where I think some things that are going to be coming maybe in the next 25 years, right? In 1985 to 2010 is 25 years. Some of these things are going to happen a lot more quickly, and some of them are already happening. But as we move forward with the provisions, maybe we'll be looking at this. We're going to continue to improve in the provisions, and I call this sort of tweaking. So new things that come up, we're going to change equations, or we're going to change words to make sure we're clearer, or we've got a new information that comes out of research or other studies. There's going to be expanded use of nonlinear response history analysis, and both for demand estimation on our members as well as performance demonstration. I think there's also going to be a trend toward increasing the demand for higher seismic performance of systems, and not just sort of basing it on, you get one earthquake out of your building and then you've got to knock it down and move on. I think our owners in society are not going to really be accepting of that as much as they have been in the past. So this is only going to continue to happen more and more in the future. There'll be new systems considered and new concepts for design that I think will be moving forward. So I'm going to talk a little bit about all those topics as we go forward. A lot of the modifications and this tweaking I talked about, I hope will help to reduce cost. There's work going on now at AISC about column splice requirements and demands and base column bases. Again, we've been fairly conservative with those. We might be able to back off a little bit on those. We may also be able to be better define what kind of disturbances in the protected zones you can leave in place and don't have to deal with. We're also going to be looking at non-wide flange moment frames that might use ACSS sections. So some of the research that our new research fellow is going to be working on. We're also going to be new research results on special concentric brace frame, gusset plates, and the like. Composite elements are continuing to be worked on, walls, eccentric brace frames, and CFT columns. I think we're going to continue to improve the provisions in those areas. We're also working on improving the consistency of the reliability level and the sort of safety factor, if you will, in our capacity-based approaches. What we've done over time is sort of each individual system has developed the capacity requirements, not in a vacuum, but sort of individually. and we may not be very consistent about the beta factor or the safety level that we're we're getting out of those designs. So we kind of step back, and Greg Deerline at Stanford is looking at these systems or these requirements to see how we can bring better consistency and overall reliability to our systems. This idea of expanding nonlinear response history analyses in tall building design, it's become very common for performance-based earthquake engineering to limit the size of the members and really understand the requirements. And it's also been used pretty heavily in major seismic retrofits. You can do a much better job of estimating column requirements. I mentioned this idea that in eccentric brace frames, if you had a 30-story eccentric brace frame and you had to do 1.1 times RY in every link all the way up the building, well, guess what? Those columns are just going to get humongous and probably not an efficient system anymore. The reality is once you get into systems that are that tall, you've got multi-mode effects going on, so you're not going to yield and strain harden the system simultaneously all the way up and down the building, so you're really overestimating the load on those lower tier columns. So nonlinear response history analysis will allow you to get a better handle on that and limit your sizes and make your systems more efficient. There's improved provisions in ASCE 7-10 to help us with doing that. And generally these are going to be dealt with using peer review, since it is a fairly elaborate procedure to work through that. And future provisions are going to be pretty hard to write in very clear terms that apply in all cases. I mentioned performance-based earthquake engineering. It is on its way and being implemented in many locations and cases. The Los Angeles Tall Building Structural Design Council has some provisions on performance-based engineering of tall buildings that came out in 2005, 2008. City of San Francisco has an administrative bulletin in that regard as well. The PEER guidelines, PEER, the Pacific Earthquake Engineering Center, is also developing some performance-based guidelines for tall buildings. These have generally been used for demonstrating equivalent performance of structures to what the code intends. There's usually two levels of design that are checked: a service level at elastic forces or elastic response, and a collapse level for the collapse prevention level, where you're using this nonlinear response analysis to demonstrate that you don't have a collapse issue. Also wanted to mention ATC 58, which is a major effort that FEMA's funding related to the comprehensive development of performance-based earthquake engineering. I do think that the owners will be starting to demand higher performance over time, more than they even do now. It's not going to be good enough to, like I said, to walk away from a building. In Chile, there are a number of buildings that went through the earthquake a few months ago, that some of them had only been in operation for a couple of months. Some damage to those structures, but the major problem is that they're leaning out of plumb, 1 to 2%. So you've got a 30-story building now that's leaning over like this. The idea of trying to push that back into place is a fairly daunting task. So you can imagine what the owners thinking. Invested all this money in this structure, and then now it's the Leaning Tower of Santiago or something like that has to be now dealt with. So I don't think that's going to be an acceptable result in the future, and for many structures. And at best right now, immediate occupancy performance, that I factor I mentioned a long time ago, is really an indirect way of getting toward immediate occupancy. And it's been rooted in about 35 or 40 years of codes. Hard to blast it out of there. It really doesn't get us to what we really need for immediate occupancy. A couple things that aren't addressed in any standards yet are how to deliberately designing to avoid residual drift. So some mechanism that will help to kind of rewrite your structure, bring it back to plumb after the earthquake. And then what happens if your ductile elements get pretty beat up like you designed them to in the earthquake, and you can't use them again? Which in a lot of these systems, it's not going to be simple to pull out the eccentric brace frame links after an earthquake. So this idea of having replaceable fuses that you can then swap out after the earthquake and have it ready for the next 500 years or longer. What about systems that rock? Right now, the provisions assume that your structure is anchored to a foundation and you really can't take advantage of rocking. But rocking can definitely be your friend. It can limit the loads that are put into the structure. And, generally the earthquakes go in both directions, so it's going to pull you back. If you do kind of lift off of the columns in your lateral frames. Can we control that rocking, though? Obviously, we don't want to let it get out of control and then lead to overturning. How do we design the rest of the system above the rocking elements? How strict should those requirements be for ductility? Do we need much ductility if we're going to let it rock? And what's the impact on adjacent gravity systems? There's obviously deformation compatibility issues when you go from the lateral system that's rocking to the gravity system that just wants to kind of move horizontally. So there is some work on this, and I'll talk about it in a second. A couple of examples here. In 1977, actually, Professor Clough at Berkeley did some tests on simple rocking frame, and on a shake table demonstrated it's a fairly benign type of response. Got some very simple results that seemed to make sense. Went through a number of earthquakes with basically no damage. There's been some applications in the field. I've shown one here that an office from San Francisco, Tipping Mar, has done, where they've allowed a system to rock with connections to angles that then are the elements that control that rocking, and potentially if it uplifts the column enough times, maybe those elements will need to be replaced after the earthquake. The one on the right is some research at Stanford and University of Illinois at Urbana-Champaign, which incorporates both rocking elements as well as some post-tensioning to bring the structure back into place, which I'll again talk about in a second. When I talk about self-centering systems, so this is that idea of possibly incorporating into our designs a mechanism that pulls us back to plumb after we've been pushed out of plumb by the earthquake. Luckily many of the earthquakes don't tend to leave many buildings out of plumb, but there's no reason that they can't. We do have some limited ability to self-center in our structures, and gravity frames in steel buildings do have an ability to self-center, like I mentioned before, but we really don't ever calculate it, so it's hard to make sure that it's going to be there when we need it. And in some cases, there may not be a whole lot of gravity columns in the system to help with that, so you need to be thinking about that. Again, what are the R factors should we use? Can we go above the sort of glass ceiling of an R of 8 if we've got all these bells and whistles put into our system? And then how do we deal with all the other parts of the higher performing systems? A couple different approaches to these have been done. The slides on the right are moment frames with self-centering elements in them. In this case, post-tension strands that have an ability to pull the frame back. The nonlinear response is taken up in angles at the top flange and the bottom flange to take the rotations of the earthquake, and then there's an ability of that post-tension frame to pull it back. One of the key things about these systems is they have what we call a flagpole hysteretic response, and the flagpole is that vertical piece that is the self-centering piece at the end that brings you back to plumb. The slide on the right is the work at Stanford and University of Illinois at Urbana-Champaign, where the yellow elements there in the center are the sacrificial elements, the ductile elements that are going to take all the deformation demands of the earthquake. And then we've got two rocking frames on either side with vertical post-tensioning at the center, which are the sort of black elements between the red braces that would have a tendency to bring you back to plumb. So some concepts, I think, for the future and for true performance-based and immediate occupancy types of designs. Some other systems I call mix and match. Right now, if you declare that you have a special moment frame, the entire moment frame has special connections, special moment frame connections. If it's an eccentric brace frame, all the links are ductile, or special concentric brace frame, you've got all special concentric brace frame braces. It's unlikely when you do demand analysis using nonlinear response histories that all of those connections are going to have similar levels of demand on them. In fact, some of them are going to be quite low, others are going to be very high. But can we get to a point where we believe our analysis enough, and you'd have to do many analyses to verify this, I think, that we could potentially, say in a moment frame system, have some that are special, where we think we're going to have the real high rotation demands, some that are intermediate, and some that are ordinary. There's obvious economic realization of economic benefits from being able to do that. Finley Charney at Virginia Tech has done some work on this that suggests it's viable. It's obviously going to be, at this point, required to do nonlinear analysis to do demonstrations of that. But that's, again, an idea maybe for the future. System validation and verification. FEMA 695, which is now available, is based on the ATC 63 document. This is the first time that we have a document that will qualitatively let us demonstrate performance of new systems that are being proposed for the code, or for major changes to existing systems. In the past, it's sort of been, comparing like systems and, the old smoke-filled room approach. This gives us a qualitative basis, or a quantitative basis, obviously, to do that. Some of the key things that are going to have to go forward is how do we use this document, how to establish these provisions or these new provisions, who's going to accept it, how are they going to go through that process. So those things are going to be worked out as new systems come forward. So just to wrap up then, documents that you need for seismic design with AISC and steel. The 2010 provisions, again, are available via download, AISC 341. That pre-qualification connection standard is 358. That's also available for download for free if you're an AISC member. And then the main specification, AISC 360. There's also the Seismic Design Manual, first edition of which was completed a few years ago and is available for purchase. And the 2013 edition is being worked on. I would suggest that you consider the design manual. It has some nicely worked out examples for different systems, including R=3 systems for lower seismic zones, goes through connection design, etc., in a very complete and rational format that you can follow. And I think it's a useful document if you're just getting into seismic design of structural systems. My voice didn't make it, sorry. So I think just to wrap up then, we do have this single point of responsibility to eliminate duplication and confusion in seismic provisions now that allows us to incorporate new information as quickly as possible. We think the 2010 provisions will help us move forward and clarify and streamline and make more transparent the documents. We also have updates including the AWSD 1.8. We will continue to try and improve the provisions in the future, and new systems will be brought forward, new performance, and lots of analysis. As the computer programs get more and more robust and fast, we're all going to be doing more analysis than we've done in the past. And we do definitely want your input, recommendations, and to improve the provisions in the future. With that, I thank you.
Well, with that, we've exhausted our time, and we've also exhausted Jim's voice. So we'll give him a break. Anyone with a burning or maybe earth-shaking question can come on up after the session, and Jim will still be here. I'll close by remarking that the Higgins Award is named for an AISC legend, Ted Higgins, who has quite a legacy of his own and quite a legacy through all the people that have received the award since it was named in his honor. And I thank Jim for extending that legend with his own contributions to it. So please join me again. Thank Jim for his presentation.